In this video, we're going to talk about anomaly detection, specifically using Local Outlier Factor. And so what we're going to do in this video is quickly explain the LOF method in an easy to understand form. Okay, so let's get started. So what is anomaly detection? It's an unsupervised machine learning approach to find outliers in a data set. Okay, so you see a data set here. Features are x1 and x2, and a whole bunch of points in that space. Anomalies are considered to be the extreme outliers. So here we have 4 such extreme outliers, and this is the main part of our data, which we might do some other machine learning tasks such as clustering or what have you. What we want to do is identify these 4 outliers, and we could either remove the outliers once we find them, or inspect them to find out if they have a suspicious origin, okay? And in particular, the applications of anomaly detection include things like fraud detection, network intrusion, and so on. So you can imagine all of the different applications that would require anomaly detection. Now, why do we need to consider LOF? Okay, there are a variety of different anomaly detectors out there. What's so special about LOF, and why do we even need it? Okay, consider the case where we have 2 clusters. Here's 1, here's 2, okay, and they have different densities. Okay, then we can identify 2 types of outliers, global and local. Now, the global outliers, which we should refer to as anomalies, are easier to find because they're quite isolated. So in this set of data points, this point here is really a global outlier because the distance from this outlier to all of the other points is fairly large, and both this cluster and this cluster would agree that this is an outlier. Okay? On the other hand, we have local outliers, and it's local in the sense that to this cluster, these 2 points, more so this point than this point, but these 2 points look like outliers relative to this cluster data because it's very dense, and so these 2 would be out here. On the other hand, this is a sparse cluster, and so the distance between this point and, say, this point here is about the same as this point and this point here. So if we use a distance-based anomaly detection technique, we're going to either include all of these as outliers and this point, or we're going to neglect this point and also neglect all of these as outliers. So distance-based methods like k nearest neighbors won't really work here, okay? And so local outliers are trickier to find because they are near clusters. And so that's the key to the whole LOF method, okay? If there are differences in the density of points in the different clusters, how do you detect this local outlier or this one, per se? Okay? And the answer is we use LOF because the basic idea is to use densities instead of distance. Okay? Keep that mantra in mind, density instead of distance. Okay? That's the key to LOF. So use the densities of the k nearest neighbors to decide if a point is an outlier or an inlier. Okay? So with that, let's dig a little bit deeper into LOF. So how do we find local outliers using LOF? And by the way, we try to find local outliers, but in the process, we'll obviously find the global outliers, right? So the way we do it is we use the densities to compute a score for each point. And then we use that score to decide if it's an outlier or an inlier. So here's a set of points, 3 in a cluster and 1 seemingly an outlier out here, okay? So how do we calculate the score for this type of setup? And so let's label these points A, B, C, D. And let's say we're focusing on this point here, okay? So what's the score that we would use to assess the outlierness of this point? And it's given by this, okay? This looks complicated, but it's actually very simple. We take the density of B, C, and D, and we average them, and we divide by the density of A, okay? So why would that work? Well, if the density of A is very small and the density of B, C, and D average is large, we get a large score. So in essence, a high score means that we're dealing with an outlier, and a low score means we're dealing with an inlier. And we're going to have to define a threshold that separates the outliers from the inliers, okay? So just to repeat, the score of the point of interest is defined as the average density of the nearest neighbors with respect to the density of the point you're interested in. So the next question is, how can we estimate the density of a neighborhood around a point? Well, it depends on how many points we consider as being in its neighborhood. So for simplicity, let's say k, the number of neighbors, is equal to 3. Then we can look at a point of interest, say A, and look at the 3 nearest neighbors, and whichever is the furthest one away, the third one, the kth one, which is the third one, that will define a circle of radius given by this distance here, okay? And that's going to be a high density region. Now contrast that with this, where the point of interest is in a neighborhood that's sparsely populated by the 3 nearest neighbors. So the region of interest is going to be this region, okay? And that would be a low density region. And finally, just for completeness, we have a point of interest here with 3 neighbors and the third point being here, so that defines a medium density region, okay? Now, how do we convert this into a density value? Well, what we do is we say, take a look at that distance, take the reciprocal of that, and that will be our density. Or in this case, take a look at this longer distance. If we take the reciprocal, we get a lower value, which means a lower density. And in the third case, it's this distance, which would be a medium density case. So that very simply is given by this equation. The density is equal to 1 over the kth distance. This is the kth distance here, kth distance here, kth distance here. We just take this value and plug it into our previous equation for the score, and that'll give us our result. So let's go through a simple example of how we would compute the density for point A in this particular example. The way that we would do it is, instead of using numerical values, let's use H for high density and L for low density. Okay? Then the score for A would be 1/3 of high, high, high for B, C, D, they're the nearest neighbors, divided by the density of A, which is low. Okay? So if you have 3 high values and you divide it by 3, you get H. H over L, high over low, is going to be much greater than 1. And if it's much greater than 1, that high score implies an outlier. But let's do the same thing with the other 3 points, starting with point B. In this case, the 3 neighbors of B are, of course, C, D, and E. And what we want to do is take the average of the densities of the 3 neighbors, okay? So over here, the score of B is going to be 1/3 high plus high plus high. These are the densities of the 3 neighbors. And of course, they're actual real values. We're just representing them by their magnitude, divided by the density of B, which is also high. And therefore, when you work this all out, it'll average around 1. Okay? And this low score implies an inlier. Okay? Now, the same thing can be done with all the other points in this figure. Let's just do one more, the score for C. So C has neighbors B, D, and E. Okay? So we take the densities of B, D, and E, that's high, high, and high. We average it, and we divide by the density of C, which is also high. So again, we get roughly 1. Okay? The exact value here is 1, but of course the numerical values will make it roughly 1. But a low score implies that we have an inlier. Okay, so any score about 1 or less is going to be an inlier. Much greater than 1, that's an outlier. Okay, so that's the basic idea of LOF. But unfortunately, this kth distance that we've been using so far has a problem. And that is, what if we have all the points in the neighborhood scrunched in one area, except for the kth one, which is a far distance away? It'll look like that's a sparse region when it's actually a dense region. So we need a different way to do density calculations that's a little bit better than that. Is there another way to estimate the density of a region? Of course there is. There are multiple and various different ways of doing that. Let's assume that k equals 3 again. And now we have the same setup as before in this high density region, except the circle is a little bit smaller. And why is that? Is because we're going to average the distances of the three neighbors. The same thing here. Instead of the circle being way out here, it's shrunk a bit because we're averaging the distances to all 3 points, and the same with the third case as well. Okay? And what we end up doing is looking at these 3 distances, averaging them, we get this. We take these 3 distances, we average them, we get this. And these 3 distances here, average them, we get this. So we always have to sum these distances up and then take the reciprocal. Okay, so now the density is going to be defined as 1 over the average distance from the center point A, in this case they're all the A's, to each of their nearest neighbors, and we take the average of that. Okay, so this is our replacement, or our improved distance calculation, and therefore the density is going to be a little bit more accurate. Now, this approach also has its own problems in that if all of the points are very close to each other, this density tends to blow up. Okay, so what we're going to do is come up with a wholly different approach, and LOF goes one step further by combining the 2 different approaches. But there's a twist to the plot here. The density is based on the relationship with the neighbor rather than just the distance to the neighbor. Okay, so let me explain what I mean by that. Let's take a look at this scenario. Here's a point A that we're interested in, and there's another point B. Now, the distance between A and B is quite large. Okay, so we're going to accept that distance as the relationship between A and B. Okay, use exactly this distance. But look at this one. Here, our A and our B are very close. In fact, A is part of the neighborhood of B. Okay, and so in that case, we're not going to accept this small distance because it'll be statistically unstable. We're going to smooth it out by taking the kth distance of B. So we either use the actual distance between A and B if A is outside the bounds of the neighborhood of B, or if A is inside the bounds of the neighborhood of B, we use the kth distance. It's a hybrid method, but what we're going to do is we're going to say the reachability distance. So now we're defining a new term. The reachability distance between A and B is the maximum of the distance, actual distance between them, or the kth distance of B. Okay, either this or this, whichever is larger. Okay, and then that will be our distance metric that we will add up, take the average, and take the reciprocal of. All right, not the actual distance, but this reachability distance. You know, the reachability of A to B here is large, the reachability of A to B is small, so we're going to take this value instead of the actual distance, right? And now, instead of the density, we have the local reachability density. Okay, we're going to name it something else because it's a different definition of density. And then the real LOF score of A is the average of the LRDs of each neighbor divided by the LRD of A. But conceptually, you can think of it as the average densities of the neighbors divided by the density of A. Okay, so that's the essence of the LOF method. We're working with densities, but we're going to carefully decide how those densities are going to be computed, taking into account statistical fluctuations of distance calculations versus a smoothing effect that we can get by using the kth distance of the neighbor. Now let's look at some results to conclude. Here's one cluster with a bunch of outliers around it, and you can see that the scores of these outlier points have been represented by a circle of radius that depends on the score. So there was a large score here, a medium-sized score here, and a very small score here. But you can see all of these outliers, especially the ones in the immediate vicinity of the cluster, have been identified. And in that sense, it's a local outlier finder. I like to call it the local outlier finder instead of local outlier factor. Okay? And finally, just to do a little comparison with the KNN method, how does that perform on the original data set that we looked at the beginning of this video? And the answer is it thinks this is an outlier and it thinks this is an outlier. And that kind of makes sense because it's looking at distances, k nearest neighbor distances, right? And so this is clearly an outlier, but it also says this point is quite far from the other points. But look at what LOF does. It finds two local outliers and one global outlier. Here's the global outlier and here are the two local outliers that we talked about right at the beginning. To conclude, let's just look at the key highlights of the local outlier factor approach. It uses relative densities to separate inliers from outliers. In fact, it takes the ratios, right? In order to do that, it first determines the reachability distance for each point based on the maximum of the actual distance or the neighborhood distance. It uses that value to find the local reachability density, the LRD, of a particular point. And that LRD is the density associated with the neighbors, not itself, the neighbors, okay? And then it computes the LRD of all of these neighbors in the same way, and then it computes the LOF score by taking the ratio of the two. And then finally, you have to use a threshold or give a contamination factor in order to separate the outliers from the inliers. Okay? Now, we published a book called Fundamentals of Robust Machine Learning, Handling Outliers and Anomalies in Data Science. And there are a variety of different topics described in this book, and I encourage you to get a copy. We'll be putting out a lot of videos based on this book going forward.